going on. Also, they introduced the opportunities for PhDs and musicians and university. And you know that university is one of the finest university in Australia and in the world. So and the topics here is very attractive and very interesting, and I think that also you interested in those. And this is a job introduction talk, so basically that please record whatever you think is relevant, and feel free to reach me to get the contact number of the professor. Maybe you have a further discussion or talk whatever it is, right? So I'll break orders, so the floor is yours. Thank you. Thank you. Thanks so much. Yeah. We had a laser pointer. If this is noise, if not, I can. Cũng có laser pointer để mình vẽ.
Có phải em đi không quá.
Yes. And I'm sorry, this time of year, okay, so we try with some final exam and some of my colleagues. I think that I pass on the information they use on the topic later. No worries, sorry for any of the words. Yeah, so we can start with yes, thank you so much for hosting like visiting and also the seminar here, because this is our great pleasure. This is our first time to visit this country in China, and also we are quite enjoying the visiting and warm hosting with us. I would like to give a brief introduction of our research work, and mainly focus on catalysis. And this is most of the common research coming with us. Okay, but before the talk, I would like to give a brief introduction of our university. This is the oldest university in Australia, the first university. And now, this year is 175 years old. So, we already 175 years old. The University of Sydney is located in downtown of Sydney, the most expensive and beautiful place in Australia. And this is our main building. So we have named for this building the Harry Potter building, because movie on Harry Potter, so use these buildings as better. So we are quite a big university, so we have more than 75,000 students. And 30%, so over 20,000 students are international students. So we are quite international. And we are currently, we are always good in the ranking. We rank, this is last year ranking, but of course new year ranking coming out. So now in the US news, we are ranking #1 in Australia, and in the conference we are ranking #2. But normally we are ranking top 30 universities around the world. So as I mentioned, we have many PhD students, and we have many international students. In engineering, for most of the PhD students, they are international students. So over 99% PhD students in engineering are international students. We offer very attractive the PhD scholarship because we want to look for the talents from the global collaboration. So it's, you can see here, this is now, Sarina will give an exact number later. So it's over 40,000 tax-free living costs for the scholarship class. It's around 30,000 preparation fee, the scholarship. That means the full scholarship is around 100K per year for PhD student. And for postdoctor, now the salary is around 150,000 per year. So this is ranked the top in the world, the top 2, the highest salary for the postdoctor in the world. Another one is Switzerland. Switzerland and Australia, they're both most expensive and also highest salary for the postdoctors. We are also looking forward for the visiting, whenever visiting student or visiting like academics to working with us. So if the Vietnam government support you, and then we will top up the living cost in the city because it's expensive place. And also if you have no funding from Vietnam government, and we also will provide the living cost from University City, because now the Southeast Asia is our university strategic focus on collaboration, because most recently, 2 years ago, the University of Sydney built a Vietnam Research Center in Ho Chi Minh City. Yeah, in this city, our president come here for the opening ceremony 2 years ago. So the collaboration between Vietnam and also this area with our university become closer and closer. So we have 2 centers focused on one area. This is only for the Southeast Asia. We have a Southeast Research Institute, Southeast Asia Research Institute, and the Vietnam Research Institute. We have both 2 in this area. So this kind of collaboration will be open the gap for both meeting and the collaborations and also mobility in our university and also Australia in the near future. Okay, so now I go back to my group introduction. My group is mainly focused on reaction engineering, combined catalysis, materials, and the spectroscopy to understand the material, how their performance during catalysis, and also to link the structure and also the performance correlations with the computation knowledge. And then we use them applied for energy, like fuel, hydrogen, biomass transformation, hydrogen carbon transformation, and also for the environment, like CO2 capture and conversion, like methane conversion because of greenhouse gas, and waste plastic conversion, and also upcycling. We also do some MOX and carbon dioxide to produce uranium, like not only carbon cycle, we also do the nitrogen cycle, and also we do the plastic cycle, and like that. So most recently we are working for the bio and the health, because we are moving a little bit into the biocatalysis, to the inland catalyst, because for the future, fundamentally if we want to address the sustainable problem, we need to learn from nature. And also, first of all, if we move to the inline and the cells, and then naturally we go to the health topic. So like a cancer treatment, I will give a very brief introduction later about what we are doing, how to combine the catalysis research to the cancer, like prevention and treatment. So we are mainly focused on 3 stages, like nutrition for the prevention of the cancer, and then sensor to find the cancer. And finally, we use the photocatalysis method to treatment of the cancer. So yeah, recently we published a paper in the thesis, Food Science Technology, to discover which kind of the food compound, nutrition compound, can good for your can limit the cancer growth, and also which kind of the food will help the cancer growth. And based on that, we developed the nanotechnology, which will be a porous material or functional material which are able to deliver the food function group or nutrient go to the target place, which can help us to improve efficiency to minimize the cancer growth. And in America, the 30% in the past 10 years, when they apply the healthy food for the cancer prevention, 30% of the cancer will be reduced. Reduce 30%, save lots of the medical money. And then, but this food take from every day, we know because they have functions from the stomach, the acid get dissolved in it. So only small function group can go to the cancer treatment. But we want to do the nanotechnology for food delivery. And to help improve efficiency of the food. But this is a bit more the catalyst of we do. So very recently we are working together with the local industry, SunBio, to develop the cancer prevention food, the healthy food for the market. And after the prevention, we think about the sensor, how to detect the cancer at the early stage and a quick stage, and which can help us to very fast response at the early stage, help the treatment. And if we look about the DNA, because this is very, whatever RNA or DNA, both can identify the cancer cells use like DNA, whatever this kind of the most fundamental ways to identify and compare the healthy cells. If we look about that, there are construction of the nucleic acid with the amine group. If we have an amine group, then that means we can generate the chemical interaction between amine group and also sensors, because amine group is very active nucleophilic, right? So in this case, we developed the different type of nanoparticles which based on the GOD, and also this is GOD based, which generates use the amine group to link with them. Then we are able to use this amine group to interact with amine group coming from the DNA, the cells. So in this case, they will have a different interaction between the healthy cell and the cancer cell, and easy for us to identify them. We also use the cheap one because GOD is too expensive. We use the biomass and to make the carbon dots. And then we modify the carbon dots with the amine group and also acid group as well to generate a multi-functional group which are also able to interact with the nucleic acid coming from the DNA, and which are able to have the cancer cell in the body. It's very sensitive and very high selective. So when we got a cancer cell, we tested that. We're also working for the treatment, because cancer cells like normal cells, so they're not able to survive when the temperature over 40 degrees C. So this is the reason when we got a fever, we need to cool it down. Otherwise, the cells will be damaged, whatever healthy cell or non-healthy cell. So we are thinking about the photocatalyst, if we irradiation of the solar, and which can generate the heat. So for some specific nanoparticles, like plasmonic particles, we'll introduce later. And then this kind of heat in the some specific area, which around the cover around the cancer cells, and they will increase the local temperature 7 degrees C, even higher. And think about the body temperature 37 degrees C, and then hit about 44 degrees C around the cancer cell, they will be killed. And they do not influence the other healthy cells. So in this case, we are able to kill the cancer cells. So recently we have developed new materials like gold material, which have the sphere, nanoroll, and the star. And then we find during the modeling, the star one which can have accumulated the hot electrons in the one point, and then which can increase the temperature, highest temperature around 10 degrees C. So this means which can like burn the cancer cell wall and then kill the cancer cells. So we already published and realized this kind of functions, and then we already tested in the animal, and then we'll go to the next stage test. So in this case, we are able to link the catalyst with health research, because this is your chemistry and human beings lots of chemistries. The reason is this picture I take from the German Deutsche Museum, German museum in Munich, the world's largest science and technology museum, and which gave me very strongly impressed about the conclusion. Yes, in our body, the mini chemistry, mini catalysis, whatever it is, biocatalysis use the enzyme to dissolve the biomass, the food, to provide energy, and also in the blooding system. So we have iron to catalyze the oxygen to generate the carbon dioxide, generate energy for ourselves. So the many fundamental catalytic research is to minimize microchemical engineering inside the body. So we use our this kind of understanding for our chemical engineering also can help us to do research for the body. But it was a past about the bio. I don't want to talk too much. So now I want to talk about our catalytic research. So today I want to focus on one area is we are able to use characterization technology to build a link about the structure and the performance. So for research, we always want to discover what this world looks like. This is fundamental research. But for the catalyst, we also want to discover how this catalyst looks like. But most of the catalytic center in the nano range, whatever this is nanoporous material or this is nanoparticles, because in the active size, normally in molecular level, in a very small size. But in this kind of small size, use our normal observation, difficult to understand the structure or morphology. then we need to use physical tools. So like TN, we are able to identify how the morphology is another side. So in this case, in our university, we developed very outstanding and also state-of-the-art research facilities. So we have a world-based TN facility. So the dual-cis correction TN, which are able to identify the 60 PN, this kind of the area of the material. So that means we are easy to identify the single atom. So we are able to, now we have the in situ holder together with the TN, so we are able to identify the dynamic of the single atom moving. And also we have an atom block, which can give you a 3D imaging of the nanomaterials in the composition and also the structure. We have a high field NMR, 800 megahertz, so which are able to help us to identify the structure of the molecules, whatever is biomolecules like the protein or this is materials. We also have near atmosphere pressure, this kind of experience to identify the catalytic reaction in the system. We also have another other tools like in situ TN, in situ IR, and in situ like Raman and other in situ tools to help us to identify the catalytic reaction under the working condition. So for a catalyst, it's quite simple because the majority of the chemical industry rely on is a catalytic process. Now the catalyst contribute to 30% of the global GDP. So for the daily life, whenever we drive the car, you need the energy. Whenever this energy coming from the fuel, the diesel or the gasoline or the hydrogen, so all coming from catalytic process. And if we use a battery car, and then for the battery materials, some of them are from the catalytic process. So fibers, paintings, daily chemicals, even plastic bottles, all from the catalytic reaction to drive the feedstocks or the monomers. So therefore, this is significantly important for us. But for the sustainable development, so we need the catalyst under control because the nanomaterial is a solid. If we are not able to understand, discover their structure, then we didn't know how to make the best one. Like our build a building. Then we need to design a building, which structure is the most stable to support this building. Whatever this building, the 2 floor or 3 floor or 100 floor. The same. For the catalyst, we also need activity. This is like function. We also need the stability, like structure. So all of them will be helping us to link with active side. For example, the structure provides an active side, and then active sides drive the reaction. But the reaction tells us which kind of active side we need, and then which kind of structure we require. So this kind of a circle, we need a tool to help us to understand them. So we use the in situ and ex situ spectroscopy and microscopy to understand that, to make the overall picture, to generate a link between each other. And a link between the structure and active size is caused by the geometry and the composition. So we always want to use the tools to understand the geometry and the composition of the material, which can guide our synthesis. So today's my work will really focus on how to make different tools to understand the geometry and the structure composition to help us to work for the catalyst. So first I'd like to talk about NMR, the nuclear magnetic resonance, because this is one of the popular methodology to identify the structure and the composition of the material at the same time. Now this is very popular for the molecular structure identification and also for the other applications. So there are more than at least 6 Nobel Prize winners in this area. And for the material application, Professor Ernest from ETH3, which I did a postdoc before, and he developed the Fourier transfer. This technology can help us to identify the signal from the noise, the resonance, noisiness, and then we can get the pictures. So how good for the application? Then I just want one example is the solid acid. The solid acid, especially zeolite, the combination of the silica and alumina, both are sensitive for the nuclear magnetic resonance. and solid acid, which is dominant in the current oil refining industry. So solid acids and acid catalysts contribute to the more than 50% of the current chemical process. So one most big like applied process is oil refining. Whatever shift from ExxonMobil, BP, they use the zeolite for oil refinery and solid acid for oil refining. But in this process, you can find only 70 to 80% of the petrol oil transferred to the gasoline or olefins. So around 20 to 30% of the crude oil, they burn, become carbon dioxide to the environment. So the oil refinery is the second largest industry CO2 emission source. Who is the first, biggest one? The biggest one is the power generation. So the generate electricity, because they always burn, right? So this is the biggest one. So then we find the reason why this happened, why the emission so many carbon dioxide. So then we look about the zeolite. Zeolite not only silica aluminum material provide acidic size, they also have nanoporous. The pore size is around 0.7 nanometer. And then the molecular entry into this pore, then generate a reaction. So this pore is important to cracking and also have a negative point because it will block by the big molecule like coke generated very quick. So this is the most popular process in oil refining. The number one popular reactor in the chemical industry is the CC reactor, very high efficient. But the reaction happened in this rising tube, normally in 100 microseconds. The catalyst die because the coke generated. We need to burn the coke in this regenerator, introduce the air and burn it. And the coke burn become carbon dioxide and the catalyst is fresh just within 1 second. And then the circle to drive this reaction. So every second, large amount of CO2 will be removed by regeneration. And then new crude oil pumped in. To think about the body, the huge amount of the crude oils we consume every year. It's in the billion tons of the crude oil. And then most of them, not most, 20-30% of them become the carbon dioxide, burn to the carbon dioxide. So this is huge. So how do you solve this challenge? This challenge can have two functions. One, which can minimize the coke, minimize CO2 emission. The second, which will minimize the crude oil consumption. This is non-renewable resource. So what we do is, this is a very critical example we use NMR to identify that. So one way is we can make a big porous material, like a mixed porous material, mixed porous zeolite. So this is already published in ES, Professor Liu Long from Korea, he published a couple of the science Nature papers about this one. Another way is about we need to strong acidic size, which can broken like a big molecule to a small one in a quick way. So we are interested in that way. So we prepared one kind of silica alumina nanoparticles, which is a non-porous material, and then we use very unique methods. It's a flame screen synthesis. The flame methodology to prepare catalyst is already commercialized. So if we find many ladies here, so you use a sunscreen, right? In the sunscreen, the composition is the titanium dioxide or the zinc oxide. So this is P25 titanium dioxide, already commercialized in Germany by the DACUSA. They use this flame synthesis every year to produce several million tons of this titanium dioxide for the sunscreen. So there we find this methodology is great to prepare large amount of silica alumina. We find we can generate a high surface area one. It's a non-porous, it's great. And also we find they provide a better diffusion for both big molecules compared to the zeolite. The TOF is over 10, but for the zeolite is less than 1. Over that, we developed the in situ like NMR, solid-state NMR, to identify the acidity, how their performance during the catalytic reaction. So actually, we just generate a microreactor or microflow reaction system, fixed bed reactor inside the NMR probe. So this is the fixed bed reactor. We can have we can heat it, use the laser heating, going up to the 700 degrees, even higher. And then we have heat exchange to control the temperature. So we have we have a counter gas to flow in the hydrocarbons. So we can bubble hydrocarbons into the reactor. And the end products can go to the OMGC for the analysis. And the liquid compounds will be trapped by the cooling system. And then can do the HPC analysis. Use this methodology, we are able to identify the process side. But for the zeolite, the process side is generated by the fulminated alumina. So this is Nature already published because the silica minimum is fulminated. So this limited the density of the acidic side. It's not like liquid acids. We can put on more as we want. We can generate 100% of the sulfuric acid. But in solid it's impossible. But how to improve the acidity of that? So we are thinking about the 5-coordinated alumina. But 5-coordinated alumina, people always think about this is intermediates. So you have a very bad dispersion on the surface and it cannot be an active site. So we use the filament to generate the 5-coordinated alumina, widely popular on the surface. So you can find here, we use multi-content alumina, solid alumina. You can identify this is 4-coordinated, 5-coordinated, and 6-coordinated alumina. We find a large amount of 5-coordinated alumina. And this alumina, the population is around half of the total alumina species. It has never been observed before in nature. And the most important, this alumina can generate amorphous structure, like amorphous silica alumina, as we identified by the TA. So, but the question is whether this 5-coordinated alumina can contribute to the process side, like the sulfuric acids. Because process side working for the hydrocracking, the Lewis said no. But the papers published many years ago, they're talking about the 5-coordinated alumina only contribute to the Lewis side. So we developed a new NMR technology. This is use a proton. If the proton close to the alumina, then we can get the cross peak. Because the resonance, if two nuclei close to each other, the resonance have an interaction, and then they generate a cross peak. And find the cross peak, we have highest signal coming from 5-coordinated alumina to the process side. So this is the first time in the world we confirm 5-coordinated alumina can contribute to the process side. And we use ammonia to prove it. So we can identify this in the process side. So the density can be doubled if we have a 4-coordinated and a 5-coordinated. So we are able to double the density of the acid side. This is not unique for the solid acid side. And the most important, we are able to generate very strong solid acids by the combination of the two alumina with the one lemon. And then this is also the first time we identify the acidity similar like the zeolite. Amorphous one similar to zeolite. And this is also here activating the ammonia to generate very strong ammonia lines. So later we use a world record highest field solid state NMR is 1.5 G. This is in Florida, the world only one. We can drop to 1.5 G. Identify the bridging OH group in amorphous material. This already have debates of 100 years. So whether the crystalline whether the amorphous material can have a bridging OH group, and we identify, yes, we can generate a bridging OH group, which can contribute to the strong acidic size. And most important, this acidic size can provide a much higher activity compared to the zeolite resistance 5. So zeolite resistance 5, they have a 60 kJ per mole for each exchange for switch bond activation. For our material, we have only 30 kJ per mole, half of them, more active. So therefore, we use that for the industry test. We send the samples to the Chevron, in the US company, in the oil refining, and also in Dalian Institute, or Chinese Institute, both. So we find that we run the FCC process more than 2,000 hours test, and they show a similar performance as the commercial zeolite, USY, but they reduce more than 20 to 75% of carbon dioxide because they minimize the co-generation as we propose. So currently we are working together with Saudi Arabia company to make the pilot plant to commercialize the plant. And also for the biomass, we are thinking about the mini biomass topic here. For the biomass, because it's not like crude oil, biomass from different area, they have a different composition. Different plant have a different composition. So we need to guess the solid acid to drive the biomass transformation. So therefore, we develop a double flame synthesis methodology device which can guesstimate the large amount of silica alumina to make the gasoline, so which are able to generate kilograms in an hour. So it's very convenient. And then which tunable catalyst depend on so what's your target, the material or conversion. So we also use ALD, atomic layer depletion. This equipment is a little bit more expensive, but this equipment also can provide much more stable acidic size for the biomass conversion as well. And so recently, we use a MOF, develop a MOF material which can combine with acidity for the biomass transformation, especially for some high value, like pharmaceutical plants, for instance. So recently, we use NMR to help the biocatalysis. So for example, we identify the enzyme interaction with the MOF, how it works between each other with the solid state NMR. We find wonderful interaction help hold the enzyme inside the MOF. And also we use this methodology to help us the first time in the world to introduce use the manual interaction to catch the enzyme inside into the MOF pores and then host it inside for the very mini homogeneous catalysis now become heterogeneous catalysis. So this is very good like the host framework engineering using these solid state MOF systems. And most recently we use AI, machine learning, together with solid state MOF to help us design the new MOF materials to solve many different challenges. Okay, so previously we focused about solid state MOF and which applied in the acidic catalyst and also the biocatalyst application to understand geometry and also the structure. But different technology have different limitations. The solid state MOF cannot do all the calculations for the catalyst. So for example, like transition metal or noble metal, they have been limited for the application of the NMR because they have electron shield and magnetic influence. So the paramagnetic influence make the zeolite, make the NMR signal to be very broad, cannot detect it. So in this case, we need the XS or the IR or the TN to identify that. So originally we are developing many types of different cells for electric catalysis, for photocatalysis, for the thermal catalysis, for different XS exact application. So we are cooperating with many global famous exact facilities like Stanford, Australia, our own one, and also Diamond in the UK, as well as Taiwan, Japan, with Spring Lake. So we have access to the sequence nearly 11 months. So we have enough like facility access for in situ research. So today I would like to talk about the green hydrogen production from the seawater. So which is one example of what we are doing using in situ, combining in situ like XS together with other technologies. In Australia, we have one challenge. So the green hydrogen we promoted by the Australian government. But in Australia, we have a challenge for the fresh water. Australia is not rich in fresh water. So we only allow to use the seawater as a resource to produce the green hydrogen. But the seawater, they have lots of the salts and also chloride. So you have to make the process sustainable is a big challenge. Because the salt, when the water removed, the salt will condense on the surface, catalyst will die. So therefore, we need to remove produce the hydrogen at the same time to use the chloride to generate chlorine. This is chlorine is very valuable chemicals. So but we need a very stable catalyst because the chlorine is very precious. So metal oxides will easily dissolve by the chlorine. What we are doing, we use the carbon. The carbon is great material because they have electron conductivity, perfect for the electron catalysis, and also which are able to link with the metal to generate the hydride, the strong combination. And in this case, chlorine cannot crystal them. So in this case, we generate single element. You cannot generate cluster or metal particle on this material because any little particle, any little cluster will be poisoned, crystallized by the chlorine. So only you coordinate it inside, it will be stabilized and working in the environment. So we successfully generate this kind of material, and we use EXAFS to identify this is pure single atom materials. And then we do the catalytic reaction for this kind of seawater hydrogen production. You can see here we are running over like 1,000 hours. So normally for the chlorine like production, the electric catalytic way, the maximum is 1 hour. Normally just 10 minutes, the catalyst will die because of course if you any other material, other even non-single atom materials. But here we realize the stability for drive this reaction and produce a significant amount of hydrogen and a significant amount of chlorine. And then we use in situ to identify how it works. So we compare the single atom here and the non-single atom here. So we can find that the single atom is always keep stable during the reaction after whatever you in situ Raman, in situ IR, and also the in situ EXAFS. But for the particle one, it's crystal, and then for the liquid, we generate IUI bond, methyl bond. So this is the ritual. Okay, so I don't want to talk too much about here because the conclusion is we can generate the two products, chlorine production together with the hydrogen production. Two valuable products from our water system. And currently we already have a small device, conventional device for this one. And we our own have a startup company to commercialize this technology. We have 3 startup companies. One is for the green hydrogen, the green energy, and one for the bio, another one for the plastics. Yeah. Okay, so talking about geometry and computation. Previously, whatever NMR or the XS, this is the spectroscopy. We based on the analyze the signal and then propose modeling the structure, right? How it looks like. But we are not able to see exactly what it looks like. But only TN or microscopy can help us to see exactly the structure. So how it looks like. So nothing better than you see it, right? So if we are able to see everything in the nano range, how it looks like, then it's perfect. So therefore, we have, fortunately, Australia National Microscopy Center is in our university, in the Sydney University. So this way we have a best facility. So that means we are able to have the TN, high resolution TN, to identify this is their pore. You can see we not only identify the black one in the pore, and also each atoms around the pore, we are able to identify them. So we also can identify even the oxygen vacancy inside the material. So use this high resolution TN. So we know the catalyst always coming, activity center coming from the vacancy. Now we are able to identify them. So this is the first thing we are able to go to extremely small range, like atomic range. But as we mentioned, the material under room temperature, we do the crystallization, and the working, a totally different structure. I will show you an example later. So if we are, so in this case, we think about we needed to introduce, in situ, we introduce the gas, we heat the dampers, going to the target range. So currently we have an in situ holder, which are able to heat up, going over the 1,000 degrees C, to see the mobility change of the materials. So recently, we now one paper in the manuscript is we are first time in the world to see the movement of the single atom in the single atom catalyst on the surface and under the heating at 100 degrees C to the 800 degrees C. How they are moving, how they combine together, how they grow cluster, and what's their working stage in the reaction. So this is exactly amazing technology we have observed. So we are able to give the evidence, right? So everything is changed during the reaction. It's not a steady state. So what will happen? Okay, I give a couple of examples. Firstly, the dry forming. The dry forming is a very classical reaction. I don't want to introduce too much because of both greenhouse gas, we only get a Hd. But for this kind of tough compounds, whatever CO2 and methane, is very stable. We need the most active atoms to drive them. So we use single atom catalyst, very popular for water gas shift reaction. Whenever this is gold or the platinum, they both active in water gas shift reaction to promote hydrogen production. While the single atom catalyst is totally not working in the dry reforming. In the dry reforming, we need to activate the both compounds. One is the carbon dioxide, one is the methane. The only carbon dioxide and methane activated on the one platform, then they are able to drive the reaction go further. If they are activated separately by the single atoms, they will go back, the reverse back to the methane and the CO2. The reaction cannot go further. So we find the four nickel atoms is the minimum number of the clusters atoms to drive this reaction. So we also give experimental evidence to confirm that if this is single atom, no reaction, no performance. And if this is the four atoms together like cluster, 1 or 2 nanometers, we see the performance. But if you become particles, you cannot increase strongly. So that just means the single size is good enough to drive reaction. But the problem for a single size is it's 1 or 2 nanometers. It's sub-nano particles. Sub-nano particle is not stable. So how we are able to stabilize it? So we use nanoporous material to stabilize this kind of single-side metal. You can see it's not a steady state. It's always changing the shape. It's moving. It's like a liquid, right? The later we'll have a liquid metal. We'll talk about that. So in this case, we can find they have totally different phenomena. I do not want to go to details. We can discuss later because of time limitation. We find that this kind of phenomenon is totally different with the big particles without the pore limitation. So you can see this is chemical catalyst. You can see to 700 degrees C. The catalysts combined together become bigger one. So this is a very poor performance for the chemical one. So in this case, we just introduce nanoparticles inside the porous. Therefore, we realize the stability over 100 and also even longer. But if it's outside of the porous, it deactivates very quickly. So in this case, we develop a series of catalysts, and I don't want to, due to time limitation, not too much talk about that. And then, but change of dynamic not always good. For example, in the ammonia synthesis, if we, without promoters, the active site will be damaged. Put a promoter there, the active site will be stabilized to promote ammonia synthesis. So they have many different information coming out from running catalyst rather than the steady state. So later we combine both spectroscopy and spectroscopy for a working catalyst. And for example, we discovered that the CO2 is a bad factors for the dry reforming cogeneration, not the methane, because normally people think about methane. And then finally we find that this is the CO2. So therefore we limited the CO2 and make the process more smooth. And we also use the carbon dioxide like hydrogenation. We control use microscopy and spectroscopy. We generate the hydrogen valve on the metal surface, catalyst surface. We realize 100% selectivity for the carbon dioxide or 100% selectivity, and nearly 100% selectivity to the methane due to the control above by the atomic catalyst design. So we also realize a single atom catalyst here, like this isolated single alloy catalyst to realize the selectivity change. You can see dominated by methane, dominated by the carbon dioxide. So later, we use in situ TM to find rate dispersion of the particle size to create the support tail effects for alloy particles, which also generate the ultra-stable catalyst for the bonding. So later, we also use this concept for the matching, circles in the environment. So for example, we are able to use the carbon dioxide, like carbon cycle, carbon dioxide together with the nitrogen to produce the urine. This is the fertilizer for the farmer. So we use this methodology to develop a new type of catalyst. So to in situ synthesis, the urea synthesis in the farm, all of them. So this is a good way you can save lots about energy consumption. And also recently we devised the photo catalyst for for this kind of urine synthesis in the field, because in Australia, the soil irradiation is very good. Now we make this is small device in the lab, is a 10 centimeter. Now we already make 1 meter, this square of this kind of device, tested in the farm. So we also got a strong industry support about that kind of topic. So this is sustainable carbon factory. Okay, finally, so for a summary, so the characterization technology can help us link the structure and the performance, which can guide us to design and manufacture the catalytic system for better performance. And then thanks for the funding and collaborations, we also want to introduce our journal. This is material study sustainability, cover nearly all areas for what we are talking about here, and also the focus area in the chemical and chemical engineering and the environmental engineering. So I served as the chief editor for this journal, and Sarina is the associate editor for this journal. So this is the Q1 journal, and the impact factor is 7.9 this year, and we are aiming going up to 10 in the coming years. So now this is the open OA journal, so that's we need to pay. But we have, as editor, we have free. We are able to waive the fees. So if you have good papers, welcome to this journal. We are able to waive your OA fees. Okay, thank you for your kind attention. This is my group.
Like to have Q&A after the
Sure.
Yeah.
Good afternoon, everyone. So really happy to meet all you here. So this is our first trip to Vietnam, so really exciting. And then I would like to introduce my research in photocatalysis for sustainable chemical production today. And then we start from we start from our faculty flyer for recruiting PhD students from Southeast Asia. So this is an initiative, I think, from last year maybe. So we are focusing on this Southeast Asia, especially Vietnam or Thailand area, to offer special scholarships for those very talented students. So if you can see, our scholarship will be like around 41.7 thousand per year, roughly around 3,500 Australian dollars per month. Okay, it can fully cover all of your costs in Sydney. It's quite a good payment with full tuition fee waiver. Okay, so you don't need to pay anything. Okay, and then probably for the requirements, we probably request a GPA above 85 or maybe 90 if in 100 if you would like to apply for the university scholarship. But for those supervisor scholarship, probably we can have some flexibility in the GPA, but we're requesting a good research experience, like you probably published a paper, or maybe not yet, but you have a really good experience. Okay, and then we request English test, else at least 6.5 overall, and no subclass less than 6.0. Okay. So, and then here is the full information of this Southeast Asia PhD application. And then we have an expression of interest application step nowadays. So you can contact the supervisor directly for the project scholarship, or if you cannot, if you haven't found a supervisor yet, so you can submit your EOI first, and our HDR office will communicate with us to find you a supervisor. Okay, so then back to my own research. I worked in photocatalysis mainly based on metal nanoparticles, plasmonic metal nanoparticles from my PhD time, starting from 2010, and I continually worked on the topic till now, about like around 15 years. Okay, so it is mainly focusing on photocatalytic chemical synthesis. So different from semiconductor materials. So my photocatalytic material is mainly this plasmonic metal nanoparticles. Okay. So this is not a new material. It is actually discovered and has been applied in decorating those glass art from the very early time in Europe. So one of the examples is the Recorder's cup. So this one is a very famous art. I think it is displayed in the British Museum now. So it is made in the early 4th century. So we can see this glass cup. If we shine light from the outside, it can give a green color, and if we shine the light from the inside, it can give this purple reddish color. So this is because it is containing a lot of plasmonic gold and silver nanoparticles or their alloys, and then those nanoparticles can absorb most of these wavelengths in the visible light range. So this makes it having a very special optical property. And then the mechanism of this is discovered in 1990 as those metal nanoparticles have a surface plasma resonance effect. So when some of these metal nanoparticles, so for example gold, silver, or copper, the size of those nanoparticles are much smaller than the wavelength of the incident light. Their conduction electrons can oscillate with the electromagnetic field of the incident light. Okay? And then once this frequency of this resonance and the frequency of the light overlap, there will be a very strong resonance. And by this strong resonance, these metal electrons can get most of the energy from the photons and becoming high energy electrons. Okay, so that is hot electrons. And except generating those high energy electrons, this LSPR effect can also generate an enhancement of electromagnetic field around these metal nanoparticles. So which is here it is like around more than 20 times higher than the electromagnetic field of the light. So this part is actually very effective in interacting with cooler molecules in the chemical reaction. So we will introduce this later. So this optical property, surface plasma resonance effect, can be controlled or changed by the particle size and the morphology. So for example, in this case, the different gold nanoparticles with different sizes, and it can give different reddish colors. And then this is the color from silver nanoparticle with different morphology, so it can give greenish or yellowish color. And the ancient people have successfully found it and successfully used it in decorating the glass of the church window. Okay, so there is an earlier work that using the gold nanoparticles supported on zirconium oxide, and then it can degrade or photodegrade these formaldehyde molecules in the gas phase very effectively under light irradiation. Okay, so this is confirming that this gold nanoparticle itself can work as a photocatalyst under a very normal visible light irradiation. So similarly, those colorful glasses are similar to these gold or silver nanoparticles supported on glass. Okay, so they are actually not only a useful art, but also an air cleaner worked for many years. So if you type those keywords in the Google, so you can find the report of this work. So this is the first discovery of this independent photocatalytic activity of this plasmonic nanoparticle resource using on semiconductor as an alcohol. Okay, so we are now using this solar energy to the chemical reaction using the different ways. So one of them is changing the solar energy to thermal energy and photothermal catalysis. Similar with this thermal catalysis, and then we can change the solar energy to electricity, and then this is the photoelectronic catalysis. But our work is mainly focused on directly using the solar energy to chemical reaction. Okay, so we need potential to apply photocatalysis in a very large scale application in the future. Okay, so very specifically, I will give some examples of photocatalysis we have did. So first one is in the reduction reaction. So we know that converting the nitroaromatics to azo compound, which is a very expensive intermediate molecule in pharmaceutical synthesis, it is not an easy way. So we usually need to reduce it to aniline first, and then partially oxidize it to azo compound. So which is good enough, but we want it better. Okay. So if we use this gold nanoparticles supported on zirconium oxide, and so we're using this one for the reaction, and we can convert nitroaromatics to azo compound with full selectivity under visible light at ambient temperature and only 1 atmospheric pressure. So this means it's a very green synthesis energy saving. And then if we consider that another intermediate, which is even less stable than this azo compound, so we can get this compound in a similar way. So, for example, if we use the silver nanoparticles under light irradiation, we can convert the nitroaromatics to azo compound, which is very similar with the gold nanoparticles. But if we alloy some part of very small amount of copper into the silver and making it with an alloy surface, we found the product selectivity will change to iso-oxybenzene. So this means this alloy surface can have different performance to the absorption of the intermediate molecules and changing the reaction pathway like this. And then we said the gold nanoparticles is producing azo compound. And then if we alloy small amount of copper to the gold, and the gold copper alloy nanoparticles, then we can find we cannot get azo or azo-oxy, but we can get the aniline as the final product directly. So the reaction pathway is changing again. Okay, so this is our work that we are planning for changing this metal component or the alloy component, changing the reaction pathway. Okay, so this is briefly what our catalyst looks like. We use the commercial zirconium oxide, which is like around 100 nanometers as a support. And then our gold nanoparticles are going here like 6 to 8 nanometers. Okay. So we can see from this light absorption, zirconium oxide itself actually doesn't have any light absorption in the visible light ray or even the longer UV light. It doesn't have a light absorption. So it means the main photocatalytic activity is from the gold nanoparticle itself. Okay, so after trying a series of different reactions, we can calculate the activation and energy of each of the reactions from Arrhenius equation in the thermal reaction or in the photoreaction. Okay, so when comparing this one, we can find the light irradiation or the photocatalytic process is actually contributing to decreasing this activation energy of the reaction very significantly. And then we can have a look at the other examples. So after we already lost simple oxidation or reduction reactions, so we thinking can we use these plasmonic metals into more complex reactions? Okay, for example, switching is a reaction pathway. And then we found hydroamination of the alkyne molecule. It is hydroamination reaction. And then it is coupling between alkyne and aniline. And we found when we using the gold coupled alloy nanoparticles as the catalyst, we can get cross-coupling product under the light and homocoupling product only under the dark. So this is a light on, light off switch that we're using this light to controlling this reaction pathway. So if we comes to this detailed data, we can find from the very beginning of the reaction, the photoreaction can give a cross-coupling product as the main product. And while in the dark reaction without light, we can have the homocoupling product as the main product. And this is a very small amount of cross-coupling product here. So this is this product selectivity change of the switch is starting from the very beginning of the reaction with light and without light. So we cannot So we think about this mechanism of this reaction pathway switch, and we found under the light. So there will be more aniline molecules absorbed on this gold cobalt catalyst surface and giving more cross-covering product. And under the dark or without light, there will be very less aniline molecules absorbed on the surface, giving mainly homo-coupling product. Okay, so we can mirror this from this aniline concentrations in the bulk solution with light and without light, and we can find with the light it can decrease the concentration, but removing the light, the aniline concentration in the bulk solution can be powered. So it means it is a reversible process with light or the light off. Okay, so based on this, so we developed this project idea, or it is a ground application actually. So we can use these plasmonic nanoparticles, and under the light irradiation, it can produce very intense electromagnetic field, and this electromagnetic field can absorb or concentrate, attract these polar molecules here, and increase this reactant concentration over the plasmonic metal nanoparticles. So this is why we can get a better catalytic activity towards those reactions. And under light, those molecules can be released to the reaction. Okay, so this is developed into a ground and foundry. And then, so we can see, if compared with the thermal reaction and the photoreaction for the concentration of the reactant, so we can see if we manually increase the aniline concentration in the reaction, in the dark reaction, we get a linearly relevant reaction rate to the aniline concentration. And then we can see that product selectivity is changing from homo-coupling, here, this one, in the dark, and gradually after increasing the aniline concentration, we can see it is gradually changing to the cross-coupling product. This is because of the concentration change of the aniline. But in the photoreaction, so we can see even we initially added very low amount of aniline in the reaction, but eventually it can give a very high reaction rate compared with the dark reaction. And the product selectivity is very significant. It is from this. It is from the very beginning. It can give the cross-covering product directly, even at the very low concentration of the aniline. So this is because under light irradiation, the enhanced electromagnetic field can concentrate these anilines on the surface of the catalyst at a high concentration reaction rate. And then this is the scope of this reaction, and we can get different product selectivity to many different compounds. Okay, so we've been working very generally. And after we completed that work, so it is a light on, light off switch. So we were thinking, can we find an example of we can use the wavelength to control the reaction pathway? So for example, using the longer wavelength, red light, or the shorter wavelength, blue light. Okay. So then one of our another student find an example. So this is a sonogastrial reaction, and then we use the copper and palladium nanoparticle together in the system. So we can find when we using a short wavelength light, blue light, so we can get the homo-coupling product only. And if we increase the wavelength gradually, and we can see the product selectivity is changing from this homo-coupling product to cross-coupling product gradually. Okay, so this is very much wavelength responsive. Okay, so if in one block of reaction, if we change this blue light and the red light regularly, and then we can find this homo-coupling reaction rates and the cross-coupling reaction which is changing accordingly, very significantly. So this means we are actually controlling the reaction pathway very well by the wavelength. Okay, so this is the characterization of this metal catalyst during the reaction, and then we can give the mechanism of this and the intermediates. That this is the blue light part, and this is the red light part, and why it can give different product selectivity. Okay, so in those reactions, we also tried a lot of change part of this reaction of the chemicals in the physics feedstock to those renewable biomass things. So this is including two parts, which is the lignin to value-added chemicals and the sugars to these value-added foreign chemicals. Okay, two examples. So briefly, you will see we use the nickel cations immobilized on aluminum nanofibers as an active center for lignin modular compound to toluene and phenol. So this is a cleavage, bond cleavage reaction that we can make this biostock to chemicals. Okay. So then we can see when we add in those plasmonic nanoparticles like silver on the gold, so we can see the generated electromagnetic field under the light can enhance the absorption of these lignin molecules to the active side of the nickel because they are locating together. And then we can increase the concentration of the reactant on the active side and having very significantly enhanced catalytic activity for this lignin conversion. So for example, if we can see from here, the nickel itself or the silver nanoparticle itself, it is actually not working for this reaction too much, but if we put them together, we can see almost a full conversion of lignin to value-added chemicals. Okay, so this is the gold nanoparticle. Okay, so this is based on this outcome. Then we developed another broad application. So using this plasmonic antenna, okay, gold or silver nanoparticles to absorb light, generate electromagnetic field, and enhance the absorption of this reactant molecule on the active side, so we can promote the transition metal and catalytic performance. Okay, so it is founded again. Okay, another example. We are converting glucose or the glucose to value-added HMF compounds. Then we can add exactly same catalytic structure. So here we use chromium cation as the active site, and the silver nanoparticles or gold nanoparticle as the plasmonic antenna. So under the light irradiation, it can generate the electromagnetic field again, and then enhance the absorption of the sugar molecules to this active site, and giving a very good conversion of glucose to HMF. And then we can see, if compared with the thermal reaction at the same temperature, the light irradiation can decrease the activation energy of the reaction almost by half. So it is saving a lot of energy. Okay, so this is the detailed data. I will skip this part. And then we also find some very interesting phenomenon when we changing the active site, like we use the nickel, we use the chromium for lignin conversion and the sugar conversion. And then one of my students, when he working in the similar topic, he found there are two cations, metal cations, behaving very differently. One is gallium and one is tin cations. So these two cations can work as a photocatalyst very effectively without the plasmonic metals itself. It can be a very good photocatalyst. So he did this work separately. And then we can see from here, under the photo reaction, we can find a very good glucose conversion to HMF, like this. And this orange one is the dark reaction. So we can see the reaction is mostly driven by the light irradiation. And this kind of independent cation catalyst can give a very high turnover number. So each of these gallium cation can give more than 105,000 glucose molecule conversion over this process. Okay, so we can have a look at if we use those very complex structure of the other sugar molecules. So we can see we can have a very good conversion with very high turnover number using this catalyst. Okay, so this is why it can actually publish quite well. And then we collaborated with Professor Jun Huang for this NMR analysis and why it can work so well. So because it is under the light, the coordination environment of this gallium cation or the tin cation can go through a very flexible coordination requirement. Okay. This is the normal data of that, and this is the mechanizing. So now we are like converting sugar molecules to HMF. So we think, can we do this HMF oxidation to FDCA as well? Because this FDCA is a very important monomer for the bioplastics. So then I will give you two examples of thermal reaction, not photocatalytic reaction. Because we tried reaction for this one as well, and we found the thermal reaction is good enough. No need to adding light. Okay. So when we're using the silver and palladium alloy nanoparticles, so we can find we can convert this HMF to FDCA with a very good product yield, like around like more than 90% of this product is FDCA at only 20 degrees. Okay. So comparing with this monometallic palladium, so we can find if we use palladium only, we can get a lot of mass loss, and then we probably have a very mixture of product selectivity here, which is not ideal. And if we use the silver nanoparticles, we have very significant amount of mass loss as well. And then we can get an HMFCA and other product as a final product, which is these two is not ideal. And then silver palladium alloy nanoparticles is giving almost zero mass loss under lower temperature, and then with giving a high product yield. And then we separated FDCA from the solution like this by adjusting the pH. This is a very simple process. And then we compared it with this commercial FDCA standard, and we can find we almost get very similar pure product of the FDCA. And then afterward, we were working on scaling up this process because this is a commercially important energy-saving catalytic process for producing FDCA from the HMF. Okay, the last example. We know that ammonia synthesis usually need a very high temperature and high pressure, and we always looking for some kind of very efficient catalyst can working under milder condition, lower pressure and lower temperature. Okay, so then we collaborated with Professor Torben Dainik from the RMIT University, and then we found if we using the liquid metal gallium and then adding the very small amount of copper in, so it is like an alloy catalyst, and then we can coat it on a carbon paper to make it using it as a heterogeneous film-like catalyst, and then we can use this catalyst for producing ammonia with only like 1/5 of less heat and 98% of less pressure. So usually the ammonia synthesis needs 200 bar of gas pressure, but we can then work under only 4 to 6 ambient 4 to 6 bar of this gas pressure, and the lowest temperature it can work is like around 150 degrees. Okay, so if we compare with the current commercial catalyst, cesium and iron on magnesium oxide catalyst, at the same pressure and the temperature, so we can see the copper gallium catalyst is significantly higher in the reaction rate compared with this commercial. So it is actually a super efficient mild condition ammonia catalysis. Okay, so we can see that with only copper or with only gallium, this catalytic performance is not so good. But if we put them together, there is a very good ammonia synthesis, and then 2% is a very optimal amount of the copper. And then the reason of this is because that the copper inside the gallium is dispersed like a single atomic copper, but it has a very flexible mobility in the gallium. It can move around, and it can come to the surface to decompose hydrogen molecules, and it can go into the gallium and for the refraction. Okay. So this is all due to the mobility induced fluid structure of this blocks and making it a very good low temperature catalysis. Okay, so summary. So a major of our research is to using the solar, using the light to replace part of the heat in the chemical reaction to make it more energy saving and more green. Okay, and then acknowledgement, our collaborators, funding source, and my small research group in Sydney University, Tom is here. Okay, so, and then I think we already introduced most of the scholarship by Professor Jim Hong, so we skip this part, and thank you for your time.
Thank you for very interesting talk. I hope that the audience has some general pictures on the nanoparticles, which is the usual analysis to produce energy and valuable products. And for Professor Sabina, use it as a photocatalyst for varieties of chemicals. So now the floor is been a little bit intensive, too much information, but it gives you the broad pictures based on the two distinguished research groups at the university. So the floor is now open for questions. Any question, specific question from the student, from faculty members?
Thank you for your presentation. Yeah, really interesting your research. Yeah. So I have two short questions. Yeah. First of all, I realized your research on silica alumina. The last time I did that one, so we have protic acid breaking once. Yeah. So I don't know. Now you say that protic acid, yes, for FCC is a really good one.
Mm-hmm.
So what is ratio between protic and lamic acids in your silica?
Yes, that's a great question. So we can twin it. We can twin. So for example, for the cracking, for the catalytic cracking, we do not need too much glucoside there. So that means we are able to go to 100% pure glucoside. But for the biomass transformation, especially involve some kind of alcohol, like ethanol. So for example, in this case, we can increase to the 30% glucoside. And in this case, the glucoside can help the ethanol to remove the OH group very quickly, and then like the benzene group can help us remove the hydrogen. The can like a dual engine, the driver. I didn't list it there. We published one paper in Angewon Chemie in 2019. So we use this two sides, glucoside and glucoside, and balance with that to drive the biomass drive like involve alcohol, like ethanol, so make a faster conversion and minimize the co-generation. So this is really why we always needed to know what's the compounds, what's the reaction we need to drive. Biomass is very complex.
To control the ratio between mass and loss, protic and lamic acid. So you will change the ratio between silica and
Yes, yeah, exactly. So we have two ways to change that. So one is we can introduce the extra, like glucoside to glucoside. So they use the ALD or the RS, like even ion exchange to change the ion, like eliminate inside. Another one is we developed the double flame system. One is to control the glucoside number. Another one is to control glucoside number. So we can train it with that. It's quite flexible. Yeah.
Thank you. For the second question, yeah. So for Salina, yeah. So when you convert from fructose to SNF, yeah, you use nanoparticle on the surface of gamma alumina.
Yes.
Yeah. So the reaction, the active size on the nanoparticles, and any effects of gamma alumina, can we use another surface, or we have to use gamma alumina?
We can use other support as well, as long as we can easily immobilize this organic ligand on the surface, and then we can put our active site, like nickel cation or chromium or organelle on that organic ligand. Yep. So we use aluminum nanofibers because we use it a lot for some other applications like material structure analysis or something like that, and we can synthesize this aluminum fiber by ourselves. And this and then it has quite a lot of hydroxy group on the surface because we synthesize it like that. So it is easier to immobilize this organic ligand on that. So actually, in principle, as long as we can immobilize this organic ligand, we can use any kind of fiber support.
Thank you. Thank you.
Any questions? Yes.
Sorry. I want to ask about the first part of your presentation. The characteristic circuit light and this change this type of the circuit this transfer the energy to the reaction system. Which part is the
For which
a circuit light and change the reactive side transfer to the reaction system?
if I would, if I understand correctly, so our, like for example, the ball nanoparticle or the super nanoparticle will do some light, and then it can just generate energetic electrons, and then this energetic electron can interact with the reactive molecules in the system, and it can use a circle like that. Okay, so it is, this is for the plasmonic nanoparticle itself. It doesn't need a exciting electron from the support or the other places. It can generate this hot electron by itself, and then yeah. So it's an answer your question. Just yes, yes. The light radiation is mainly generating the hot electrons itself on the nanoparticle surface.
That's a nice question from the very undergrad students. So basically, most of the audience here, the students would like to have some brief comments to assist them to follow the response. So, Professor Jung just gave you a very excellent example of how we use the fundamental science, okay, the application, so you just mentioned that we have increased our materials. So you see the link between science, engineering, and technology, right? So basically, you want to make a product, you need understanding what the nature of the process, what really occurs, and then you take advantage of that. To make the technology that facilitates the societies and the human life activities. And any other comment? Otherwise, I will. Yeah, with the program.
Because what you are very interesting presentation, and I have one small question about the single atom pattern from the third one.
Yeah.
Because you do raw material for the application, and just curious about what is the raw materials here, and because I see the top first, carbon top first, look like graphite.
You mean carbon to realize the
Yeah.
single atom?
Yeah, what kind of carbon here?
No, we just use like for processes, we use like polymer to mixture. Yeah, polymer mixture with metal precursors, and then we do the calcination, and then they generate the graphene type of the carbon to catch the single atom with the carbon combination, like hybrid combination. And this is very strong, and also they have the chlorine, anti-chlorine, is corrosive with properties. Because they are, so they also have very good affinities for the graphene type of the carbon because they have better like electric conductivity for electrolysis compared to the other carbons.
But I see in the chapter, they want to integrate the oxygen atoms and graphite carbon, oxygen atom.
Yeah, oxygen, yeah.
Yeah, oxygen.
Yeah, this is
So
really-
how can you do that?
Yeah, because we do the calcination. We do the calcination. They have reduced some oxygen atoms in the polymer, and they prefer the precursors linked with the metal, ruthenium we use, and they're linked with the carbon. Yeah, because they have like a metal center. They stabilize them now.
Any questions? Another comment, guys, I'm very impressed, but you know that at the University of Sydney, okay, there, Professor Zhutan Serena just reviewed the state of the art experiment, so that allows you to do a lot of things inside. For example, consider the dynamic change of the current structure in terms of temperatures. So it's quite interesting. I'd like to have one comment that the experiments that help you to see what really occurs for the complex system. And Professor June and Serena just mentioned something not quite clear what the modeling and simulation tool and the AI is also exists to reveal the complex picture. So it tool does have some advantages and disadvantages, but combined so they give you the complete pictures of what is the nature of this. And basically, by the way, for the seminar, I'm doing the local conversion to an HNF too. But basically, I'm doing the modelings, and I collaborate with a colleague working on stuff like acidics, homogeneous catalyst under the ionic liquids. So basically, I'm doing the modeling, but I'm still learning the experiment for this how to prepare the chemicals. Any other comments? So, Lou, please be.
Just more question,
Yes.
because you mentioned about AI, so what is the tool for the AI you in your
Yes. Yeah, it's great. It's a great question because for AI now there are many resources, over resources we are leveraging AI to help us assist for with experiment, improve experiment. We normally do 3 ways. So first, I have one postdoctor. They use ChatGPT. The ChatGPT can help you to prepare the code when you want to sort the data and to improve the selection. Because he is mainly focused on the inline and morph interaction. But there are not many database in the applications. So he focused on experiment data to collect based on different parameters, and then use ChatGPT to help to build up a model and then to optimize the synthesis conditions. And this is one way. Another way, we also have one PhD student. They use the published paper because he mainly focused on a lawyer, a transition method lawyer, the many publications, more than 1,000 publications. And then he used also the ChatGPT can help you to build a model, and then also read the selection, the keywords to selection of the publications, and then to select. So based on these publications, you optimize. Of course, you need to set the parameters to optimize the best few categories of the potential compilation, and then we do experiment. Never 100% believe the AI. Because we also do the experiment. Some they rank number 1, not working well, but the number 3 working very well. And also based on that, we are able to find a new phenomenon inside. But this is the second application. And the third application is we mainly focus on data treatment. So for example, like TN, like NMR, we got a lot of many 2D, like pictures. And sometimes for we use for students or us, if we just watch that, sometimes we will overlook some pics and also sometimes emphasize some point by ourselves. And then use the AI just to build up a model. Just say, okay, from literature, we are able to identify the signals because they have much more information compared to us. And from AI, they will collect the information from this fig and point out whether this is noise or this is a real signal. And it helps us a lot Yeah, so these are 3 ways we are doing. Yeah. But yeah, so we are not a computer science. Right? Yeah, it's not computer science. But this is use the open resource. Now it's working. Yeah.
And you are on Python?
Sorry.
And you are on Python? Which software do you use?
The language
R,
for
the language.
the R language or the Python languages.
Okay, we are normally just use we do not use this kind of computer scientific language because we just use like AI, like ChatGPT, we are linked us. For some like FIG, we have a link with a FIG. They have an open source to deal with that, and we do not have a specific like focus on anything like that. Because all of my students, including myself, are not a computer science, so we just always use an open resource to help with that. Yeah. So yeah.
Thank you. I think that the time's up, and I know that me myself still have questions with the distinguished speakers. So maybe we will do some email exchange.
Sure.
If the audience has any question, I will forward to you.
Sure, please.
Or
Yeah.
can reach you directly. And so please join me to say thanks to